So now we go on to some other parts that also will involve quite a lot of calculation, but this one is on something else. It focuses on something else. All right. Okay, so if you refer back to your notes, page 4, let's just look at page 4. All right. Now, when you talk about nuclear reaction in general, there are actually 3 kinds of nuclear reaction. One is fission, another is fusion, and then another one is radioactive decay. Okay, each of these is called nuclear reaction, all right, but the manner in which they occur is a bit different. All right, you already know the definition for nuclear fission, you already know the definition for nuclear fusion. Now what about radioactive decay? Okay, now when we say radioactive decay is simply this process here where we say that an unstable nucleus disintegrates into a more stable nucleus by spontaneous and random emission of radiation in the form of alpha particles, beta particles, or gamma ray photons. Okay, this is what radioactive decay is. It doesn't involve a heavy nucleus breaking up into smaller nucleus. It doesn't involve 2 smaller nuclei combining into a larger nucleus. It just involves one nucleus becoming another different nucleus by emitting any of these radioactive particles. Okay, and at the same time, the process must be spontaneous and random. Okay, so you need to know the definition of what is radioactive decay, and you also need to know the definition of what is spontaneous and random in the first place when it comes to radioactive decay. So when you're talking about spontaneous nature of radioactive decay, you can just think of it as being unaffected by any external influences. Say, for example, when you want the radioactive decay to go faster, nothing you do to the environment will change the speed in which the radioactive decay occurs. You cannot just say, oh, I go and heat up the environment so that the reaction goes faster, or I go and increase the pressure so that the reaction goes faster, or I go and add some other elements into it in order to make the reaction go faster. Okay, so nothing you do can affect it. All right, that's the reason why we call this process spontaneous. It is not affected by any external influence or rather factors now. Okay, I think factors is actually a better word, right? It's not affected by any external factors. Pressure, temperature, chemical addition, catalyst, nothing will change it. Okay, nothing can cause your reaction to go faster. Okay, that is what spontaneous actually is. Okay, and then after that, we also have something called random nature of radioactive decay. Now, here is defined as it is just impossible to predict which nuclei and when it will decay. Okay, because each nucleus has constant probability of decay per unit time interval. Okay, what do we mean by that? It's something like this. Take for example, I have a sample of radioactive material. Say I have maybe 12. Maybe I make it more. Maybe I have 1, 2, 3, 4, 5, 6. Say I have 12 of this. Okay. Now, if I tell you that this one is my original sample containing the radioactive nuclei, and I tell you that my probability of decay is 0.5, what this means is that out of this sample that has, say, 12 nuclei, 6 will decay, isn't it? But which one? Now, when we say which one, it simply means something like this. Let me just draw for you another typical what I just did, you only know half will decay for your current sample, but could it be decaying like this? Or could it be decaying like this? You just do not know, right? It could be decaying in a manner like this. It could be decaying in a manner like this. Okay, so I could also draw for you some similar thing again. Okay, let me use blue color. I still have the same 12 nuclei over here. If it decays, it could also be decaying like this. Okay, so you just do not know how it will decay. I mean, you do not know which of these 12 nuclei will actually decay and when will it decay. Okay, but all you do know is that in that group of nuclei, half will decay, but you just don't know which individual nuclei will decay. That's what we mean by random here. You cannot predict which nuclei and when a nucleus will decay in the first place. Okay, you only know that in that group, only this amount will decay. Okay, and the reason why we cannot predict which and when the nucleus will decay is because each of these nucleus actually has a constant probability of decay. When we say this one has a probability of decay of 0.5, it applies to each of these individual nuclei. Okay, you won't have a case where one of them has a higher probability than the other. All of them have equal chances. Okay, that's what random here actually means. Okay, so just understand these three things, or rather just memorize the three definitions and you're good to go. All right. Okay, now then after that, when it comes to radioactive decay, there are a few kinds of quantities that is specific to radioactive decay that you will need to know. The first one that you will need to know is something called decay constant, okay, given by the symbol lambda. All right. Now, this symbol lambda, you normally associated it with wavelength from AS physics as well as quantum physics right now. You probably learned de Broglie wavelength because you're doing duality. In your current case for nuclear physics, decay constant symbol lambda, this is not wavelength. This is actually decay constant. Okay. So when you see the symbol lambda for nuclear physics, don't think of it as wavelength. It's actually referring to some other thing entirely. It's called decay constant, which in your case is this one. Decay constant lambda is the probability of decay of an individual nucleus per unit time interval. Okay, so what we mean by that is this. You see, if, say for example, I look at this sample of nuclei that I have, the number of nuclei I have is 6. The number of nuclei that have decayed is also 6. Sorry, I got this wrong. The number of original nuclei that has not decayed originally was 12. The number of nuclei that have decayed is 6. So the probability of decay, from what you've learned in maths by now, is that you take number that have decayed over the original number. This is your probability of decay, which gives you 0.5, right? So when you did this, you're actually taking delta n over n to give you probability of decay. Okay, but because decay constant is probability of decay per unit time, you need to divide by time. That's why you're gonna get this equation here. All right, because this delta n over n itself is probability of decay, and then after that you need to divide by time to get per unit time. Okay, that's what decay constant actually is. Okay, so just so you know. Okay, so this one is probability of decay. Let me just write it here. This one here is probability of decay. Right now, let me just write it. is probability of decay, then probability of decay per unit time is just going to be delta n over n divided by delta t. Okay, so this is just one thing that you can easily see now. Okay, probability of decay is delta n over n. Probability of decay per unit time, which gives you decay constant, is basically just probability of decay divided by time, giving you this. All right. Now, decay constant has units of per unit time. All right. Because you see, probability of decay itself does not have units. The units, if any, will cancel each other off. But then after that, you divided it by time to get decay constant, right? So you're going to get a unit of per unit time, which can be in per second, per minute, per hour, per day, per year. All right. So that is what decay constant is. And then after that, you would have something called activity next that you need to be aware of. Now, activity is just simply the rate at which nuclei decay. It is telling you how many nuclei have decayed per unit time. Okay, this one is telling you how many nuclei have decayed per unit time. Okay, so you want to find out the number of decay that has occurred per unit time, the decay per unit time. You just take number of nuclei decay divided by the time that has elapsed, the time that has gone by. All right. Now, same thing as before, your activity is actually measured in per unit time because number of nuclei by itself doesn't have unit. But then you divide by time, which has a unit. So your unit will be in per unit time. Again, you either be per second, per minute, per hour, per day. But there's one very special unit that is normally associated with activity. That one is called becquerel. All right. So whenever you see mention of activity mentioned in becquerel, this one is understood to mean per second already. Okay. 1 becquerel is per second. All right. So whenever you see mention of becquerel, is really understood is already in per second. Okay, so this is activity. Now, between activity and number of between activity and decay constant, there's an equation that you will use often in your calculation. That one is actually given by this. Activity is equals to lambda n. Okay, so this one is just an equation that you just need to know. There's no derivation required inside your syllabus. So you don't need to know how it came about. You just need to know that if you want to relate decay constant and activity together, they are related by this equation. A is equals to lambda n. Okay, which would kind of make sense because you see, if I have more number of nuclei, that means I will have more nuclei decaying per second. So activity increase. And then if I have higher decay constant, meaning to say higher probability of decay per unit time, this one also means that my activity would increase. Okay, so it makes sense. All right, that's all there is to it. Okay, and then the last thing that I probably need to, one of the last thing I need to probably mention to you is something called count rate that is denoted by symbol R. Now, when you see those movies or TV shows last time, especially when it involves, say, someone visiting a radioactive site, they always use some sort of device to kind of tell them whether that place is radioactive or not. That one, when you see inside the movies or dramas, you will notice that that device, if you go to somewhere that's really radioactive, it emits some sort of clicking sound, sound like that, right? So what you saw then was that if the place becomes really, really radioactive, the clicking sound becomes really, really rapid. There's a lot of clicking per second. But if let's just say the site or the place they're visiting is not as really as radioactive, you normally notice that the clicking sound is a bit slower. Okay, you get what I'm saying?
Kind of.
I know you've seen it in movies before. I think I don't know where I don't know what movie. you watch Chernobyl or something, you probably will see that. I mean, those disaster movies that involves nuclear disasters, when they want to check whether that particular site is radioactive, there's always something that they use to detect the radioactivity. And you normally see it as, or rather hear it as some clicking sound. Ta, 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 ta. Okay, the more radio it is, the more clicking sounds you hear. Okay, so that one is actually what we call the count rate. So if your count rate increase, that means you have more radioactive decay. Okay, that is what your count rate actually is. It measures the radioactive decay. How does it measure radioactive decay? By detecting the radioactive particles emitted. Okay, remember just now I told you that for radioactive decay is a process where an unstable nucleus becomes more stable by emitting radioactive particles like alpha particles, beta particles, and gamma ray photons. Correct? So when you're measuring count rate, I told you that the higher your count rate, the more radioactive decay you have. It's because when you're trying to measure your count rate, you're actually detecting the radioactive particles emitted, which can be your alpha particle, which can be your beta particle, or your gamma ray photons. Okay, so your count rate here is actually based on the radioactive particles that you're detecting. If you detect one alpha particle, you will hear one click. If you detect one beta particle, you will hear one click. If you detect one gamma ray photon, you will also hear one click. So you detect a lot of these particles in one spot, you will hear a lot of clicking sound. Okay, you can just think of it as the moment your device detects a radioactive particle, it will emit a clicking sound. So the logic here is that if something is really radioactive, that means it will decay very fast. It decays really fast, it emits a lot of radioactive particles. So your device will detect all these radioactive particles and emit a lot of clicking sound. Okay, so the device that is giving you your count rate here is actually known as a Geiger-Müller tube. Okay, GM tube in short. Okay, but the actual workings of a Geiger-Müller tube in the syllabus is not required. Neither have I seen it come out in your exam before, so I'm not going to explain in detail how a Geiger-Müller tube works. You just need to know that the Geiger-Müller tube measures count rate, and how it works is that it detects radioactive particles from your radioactive source. The moment it detects a radioactive particle, it will emit a clicking sound. And then the more radioactive particles it detects, the more clicking sound you will hear. Okay, so that's the idea behind that. All right, now there's one thing to note here also, which they will tend to ask. We know the activity is rate of nuclei decay, and then we know count rate is actually trying to measure the radioactive decay. Okay, the thing that you should note here is that the count rate will never ever be the same as your activity. What I mean by that is something like this. For example, if I tell you your activity is, say, 1,000 per second, 1,000 nuclei decay per second, your count rate will never ever detect this activity. You will only be able to measure a portion of it, say maybe 600 per second. It will never be the same. The count rate will always be less than the activity of your radioactive sample. Now, the reasoning is because of something like this. You see, if, for example, I have a radioactive source, this one here contains my radioactive source. If the radioactive source decays, it will emit radioactive particles in all possible directions in a sphere like this. But my device that is measuring the count rate, or my Geiger-Müller tube, is this one. So when it detects the radioactive particles, it's only able to detect radioactive particles in this direction only. The rest of the others in the different directions cannot be detected by the Geiger-Miller tube, cannot be detected by the Geiger tube because it doesn't enclose around the radioactive source. So it would make sense that it won't be able to detect everything. That's the reason why we say to you that your count rate will usually be less than the activity itself. Okay, so just bear that in mind because later on you will have some sort of question that relates to that asks you to explain the things. All right. Okay, so last thing to go through, I'll probably run off by 5 minutes to explain everything. Okay, now the last thing you probably need to know is something called decay graphs and half-life, which you have probably gone through in SPM before. Now, when you're talking about radioactive decay, say you have element A, once it goes through radioactive decay by emitting alpha, beta, or gamma radiation, this element A will become element B. Okay, so usually when an element is unstable and it undergoes radioactive decay, after it undergoes radioactive decay, it becomes another element which is more stable. So A is the less stable element, but after it goes through radioactive decay, it becomes more stable. Okay, it will become something else. Okay, so it's understood that when you go through radioactive decay, A will decrease with time because it gets less and less, whereas B increase with time. Okay, so if let's just say you are talking about the unstable element, the element you started off in the first place, and you measure the number of the nuclei with respect to time, you tend to get a graph shape that looks like this. It's always going to be a curve. We call this an exponential decay curve. Okay, so these are actually called exponential decay curves. All right. So anything that undergoes radioactive decays, if you try to measure the number of nuclei with respect to time, it will never be a linear line or straight line. It will always be a curved line like what you see in the diagram. All right. We call this an exponential decay curve. Now, from the curve, usually there's a particular quantity that you can actually measure, call your half-life. So in SPM, I think you learned this before. Half-life is actually the average time taken for half the nuclei in a sample to decay, or the average time for activity of a sample to decay to half its initial value. All right. So say for example, this one is representing the number of undecayed nuclei with respect to time. It follows an exponential decay curve like this. Now, if you started off with a fraction of 1, if you want to decrease by half, you go to 0.5 right over here. So the time it took for you to go to half your initial value will be what we call 1 half-life. And then from 0.5, you want to decrease to half that value, you go to 0.25. So again, that one will take 1 half-life. And then from 0.25, you want to decrease to half again, it will be 0.125, which again would take 1 half-life. Okay, so this is what half-life actually is, which is something that you would have learned in SPM before. Okay, so this is not something new. Okay, the thing that might probably be new to you is the equations that you're seeing on the next page. Okay, so just now I mentioned to you that when it comes to radioactive decay, the nuclei, when it comes to radioactive decay, like this, sorry. When it comes to radioactive, next, why do I keep drawing an arrow? When it comes to radioactive decay, you will tend to follow an exponential decay curve. Okay, so the example I gave you was if you take the number of undecayed nuclei with respect to time. Okay, now the number of nuclei can sometimes be replaced with activity. It can sometimes be replaced with count rate. Okay, so if you let's just say have a radioactive nuclei and then you want to measure the number of undecayed nuclei, the activity or the count rate with respect to time, it will always follow that same curve. Okay, like this. Now, when you have a graph that follows an exponential decay curve like this, in general, there's an equation that you can use to generalize the shape, where we say x is actually x naught exponential negative lambda t. Let's just say that this thing here is a general variable x. Okay, x is x naught exponential negative lambda t, where this one is the value at time t, and then this one is the value at time t equals to 0. Okay, it kind of is like the initial value. Let's just say, for example, x naught is this one. Okay, this is the value at time t equals to 0. All right. Yeah, the graph looks a bit weird because the 0 doesn't start from the x-axis. Yeah, but you get the meaning. All right. The x naught is actually the value at the start. Okay. So this one, your variable x can be replaced with any of this, can be replaced with number of nuclei, can be replaced with activity, can be replaced with count rate. So your equation will become something like this. Okay, so if you want to use number of nuclei, you want to use count rate, you want to use activity, the form of the equation is the same. All right, but what you would which one you would use depends on what the question is asking you in the first place. All right. Okay, so this is one equation that you just need to know. Okay, then the last thing I just need to go through with you is something called decay constant and half-life. Right, so we already know what is half-life. Is the average time taken for activity to decrease by half, the average time taken for a number of nuclei to decay by half. So the next thing I will need to mention to you here is there is actually a way for you to calculate out half-life if you know the decay constant. All right, so the half-life is actually ln2 divided by your decay constant. Okay, this one is something that you kind of need to know. The derivation is required. You need to know the derivation. The exam will actually ask you to derive out the relation. How do I know that half-life is related to decay constant by this relation? Okay, now there's an easy way to go through this derivation. You can just start off with any of these general equations here, but it will be easier to start off with, say, n naught exponential negative lambda t. Now, when you go through one half-life, when t equals to t1 half-life, your number of nuclei would have decayed to half the original value. Okay, so this one here just a true value at time t equals to 0, right? You can think of this as the original starting value. Okay, so after one half-life, your number of nuclei ought to decay to half its initial value. So n becomes half f naught. Sorry, half n becomes half n naught. So you get half n naught equals to n naught exponential negative lambda t. And then after that, the n naught will cancel off, giving you half exponential negative lambda t. Now, the next thing you want to get rid of is exponential sign here. This thing is in the way. So you've learned in maths that to get rid of that e, you need to ln both sides. Forgot to replace the half-life sign. n half n naught equals to exponential negative lambda t half life. Half equals to exponential negative lambda t half life. Okay, so then after that, this one will be ln half equals to ln e negative lambda t half life. Okay, so eventually you're going to get this. You're going to get negative negative lambda t half life. Okay, so if you go and rearrange it, you're going to get half life equals to ln 2 divided by lambda. The negative will actually cancel off because you see both sides have negative sign. So you are going to get this. Okay, ln half is ln 2 negative 1. So if you try to simplify it, it becomes what you see right over here at the bottom. So it's negative ln 2 equals to negative lambda t half life times 1. Then giving you this now. Okay, so this one here, this one what I just wanted to say was ln both sides. Okay, right. So this one is your derivation. Okay, now they tell you that an isotope of an element is radioactive. Explain what is meant by radioactive decay. Okay, so this is actually one of the three radioactive, sorry, this is actually one of the three nuclear reactions that I mentioned in the notes before. You have nuclear fission, nuclear fusion, as well as radioactive decay. So for radioactive decay, there's a full definition for it, which is actually this one. Unstable nucleus disintegrates into more stable nucleus by spontaneous and random emission of radiation in the form of alpha, beta particles, and gamma ray photons. Okay, so this one is 3 marks. You make mention of spontaneous and random is 1 mark. You make mention that a nucleus becomes more stable is another mark. And then you make mention of what does it emit. This is another mark. Okay, so that one is 1 part of it. Okay, then after that, look at B. Now, at time t, a sample of a radioactive isotope contains n nuclei. In a short time of delta t, the number of nuclei that decay is delta n. State expressions in terms of the symbols t, delta t, n, and delta n for the number of undecayed nuclei at time t plus delta t. So if you originally started off with n, and the number that has decayed is delta n, what is the number that is remaining after t plus delta t? By right, it should be n minus delta n. Okay, then after that, what's the mean activity of the sample? Activity is rate of nuclei decay. From the previous part of your notes, it was mentioned that activity is actually rate of nuclei decay somewhere. Where is it? Yeah, on the page 6. You take number of nuclei that have decayed divided by the time that has been taken. You're going to get delta n over delta t. Now, what is the probability of decay of a nucleus during that time interval of delta t? You just take the number that has decayed divided by the original number. That one will give you your probability of decay. This one is just asking for probability of decay. The next question is asking you the decay constant, which you learn in the notes is actually probability of decay of a nucleus per unit time. So actually you just need to divide by time. So it's actually just going to be delta n over n divided by delta t, giving you this. So this is your decay constant. All right. Okay, so far so good with this. Then after that, we go on to part C. The variation with time t of the activity A over sample of radioactive isotope is as shown in this figure. The radioactive isotope decays to form a stable isotope S. At time t0, there are no nuclei of S in the sample. On the axis of this figure below, sketch a graph to show the variation with time t of the number n of nuclei S in the sample. Okay, so right now you have some unknown radioactive isotope whose activity is shown here. Let's call this unknown radioactive isotope as just X. So what you know is that X will undergo radioactive decay to give you element S. Okay, so when X undergoes radioactive decay to become element S, this one you know it will decrease with time, whereas S will tend to increase with time. So what you can say is that if I'm talking about the number of nuclei X with respect to time, it by right should look like a curve like this. But if I'm talking about an element of the nuclei S with respect to time, it should kind of look like this. Okay, so that's the graph shape that you expect to see. But here you are supposed to kind of like draw it to scale. So here you have to make use of something which you learned before, which is the concept of half-life. See, this is 1 half-life, 2 half-life, 3 half-life. For your first half-life, this one was A, then it became A over 2. This one is your first half-life now. Now for your second half-life, A over 2 will decrease by half again. So this one becomes A over 4. Then the next half-life, A over 4 will decrease by half again. This one will become A over 8. Okay. So what you really just want to do here is this. You just translate the number of boxes to the diagram below. You see, for my first half-life, this one decreased by 2 boxes. So when I want to look at the element of nuclei S, which is denoted by small n here, after 1 half-life, it should increase by 2 boxes. Because here, it decreased by 2 boxes. This one must increase by 2 boxes. Then after that, if I look at the next half-life, this one I decreased by 1 box. So the next half-life here, I know I must increase by 1 box. Then the next half-life again, the third one, this one you notice that over here you decrease by half a box. So the third half-life must be increasing by half a box. Okay, so it will be these 3 points here. All you just need to do is that you just need to join them together, and then this one will be where you get your answer. Okay, so that one is for this one. This one should be pretty straightforward. Okay, next one should be page 3. Okay, next one ought to be page 3. So just have a look at page 3. Okay, wait. This one, let's just draw it properly. And increase by half a box. Okay, so this one is all right. Then next one should be page 3. Okay, so Let's have a look at page 3. Okay, now have a look at page 3. All right. Now you read the question first. Just excuse me for a minute. I go and do something for a while. Wait.
Okay.
Okay. Okay, right. Sorry for the disruption. Okay, right. Now for page 3, they tell you that the power of our space probe is to be supplied by energy released when plutonium-236 decays by emission of alpha particles. The alpha particles, each of energy 5.75 mega eV, are captured and their energy converted into electrical energy with an efficiency of 24%. Now calculate the energy in joules equals to 5.75 mega eV, right? So this one is June 2015 P42. Last part of your question, which is this one. So here they really just want you to find out the energy that is equivalent to 5.75 mega eV. So you know that 1 eV is actually 1.6 times 10 power minus 19 joules. So you want to find out how much is 5 mega eV. The small m, the big M here is actually denoting mega. So it's actually 5.75 times 10 power 6 times 1.6 times 10 power minus 19. This will be your answer in terms of joules. All right. So this one should be okay. Simple calculation. Okay, now second part is where you need to start thinking a little. They ask you to find out the number of alpha particles per second required to generate 1.9 kilowatt of electrical power. What is the number of alpha particles per second? Okay, so from this one, wait, yeah. So from this one, how much is the number of alpha particles per second? They already told you they want number per second. Now, when you read your question earlier, this one they told you your plutonium 236 is emitting alpha particles. Okay, your space probe is actually making use of this alpha particle to generate electricity. Okay, it's usually is making this making use of these alpha particles to generate electrical energy. Okay, all right. And when they change the energy of your alpha particles to electrical energy, the efficiency is actually just 24%. Whatever energy that your alpha particle had, only 24% of it will be converted into electrical energy. All right. So here, what they tell you is that when you generate your electrical power, your required power is supposed to be 1.9 kilowatt. This one is the required power that you have. You can think of this as actually your output power. Okay. So here, what you want to do is that you want to make use of your efficiency equation that relates power output and power input. You know that efficiency is power output to power input. At 24%, you change it to number form in decimal places. It's actually 0.24. Your output power is 1.9 over your input power. Your input power refers to the input power provided by your alpha particles. Okay, so you do your calculations, eventually you will realize that your input power is actually 7.917 kilowatts. This is the total power provided by all your alpha particles. Okay, then your input power can then be expanded to become total energy divided by time. Now, total energy here is actually the number of alpha particles times the energy of one alpha particle itself. That's why it's n times E here. All right. So you want to find the number of particles per second, you're actually looking at n over t. So you take your input power divided by the energy of one alpha particle instead to get the number of alpha particles per second. Input power, you already found it as 7.917. The energy of one alpha particle, you already found it as this value, because they told you earlier the alpha particles have energy of 5.75 mega eV, and you're supposed to find the value in joules. So you already found the values also for the energy of an alpha particle. So you sub in your values, you get your answer as 8.61 times 10 power 15 joules per second. Just like that. Okay, so that one is okay, pretty straightforward here. All right, then next one. Each plutonium-236 nucleus on disintegration produces one alpha particle. Okay, plutonium-236 has a half-life of 2.8 years. Calculate the decay constant in per second of plutonium-236. One important equation that you have learned before this was that you can either say that decay constant is ln2 over half-life, or you could do it the other way around, or you say that half-life is actually ln2 over decay constant. It doesn't matter which one is it, the equation is actually the same. You want decay constant, so you just use this form. It's ln2 over half-life. So ln2 over half-life, just divide by your half-life, but remember to change it from years to seconds, because the answer wants it in terms of per second. So times 365 days times 24 years, sorry, times 365 days times 24 hours times 3,600 seconds. Okay, so this one will give you the answer as 7.85 times 10 power minus 9 per second. All right, now 1 year is 365 days, not 360 days. Okay, don't multiply with 360 days. If you have watched some of the videos for gravitational field, I did explain before why you cannot use 360 days. You must use specifically 365 days. Okay,
Why would we use 360?
because some people understood it as this: there are 12 months a year,
Okay.
and then each month on average has 30 days, so it's 360 days. This one is average day in a month. It's correct to say that on average 1 year, 1 month is 30 days, right? So they actually take 12 times 30 gives you 360, so they multiply with 360 days. This one is not correct. The answer will be inaccurate. The correct number of days is actually 365 days. This is actually the correct one. So marking scheme does not accept 360. They want 365.
Oh, okay.
Okay.
Mm.
Right. Okay. So this one is okay. Yeah. So let me just make a note here. Don't use this. Right. Okay. Now next one. Next one is talking about something. Okay. For the next part of your question, they told you this. use the answers in A2 and B1, which is basically the previous two questions, to determine the mass of plutonium-236 required for the generation of 1.9 kilowatts of electrical power. How much plutonium-236 do you actually need in order to give you this amount of power? Okay, now, this one, you can actually use the equation A equals to lambda n. But before we go to that, there's something that you needed to realize from the previous question. The previous question, this statement mentioned that one plutonium 236 produces one alpha particle. Okay, so one plutonium 236 produces one alpha particle. Now your alpha particles per second, that gives 1.9 kilowatt, is actually 8.61 times 10 power minus 5 per second. You already found out here, right? Okay, but because of the fact that they told you that one alpha particle actually came from one alpha particle decaying, so maybe it's better if I rewrite this. One alpha particle, sorry, one alpha plutonium 236 decays to give one alpha particle. So your number of alpha particle per second is this. These are the number of alpha particles you're getting per second. This also tells you that the same amount of plutonium nuclei actually decay per second. So you can just say that this is also the same number of plutonium 236 that decays per second. This is actually your activity. Yeah. This is also the activity. This is also the activity. Okay. So I can say that the activity of my plutonium nucleus is actually 8.61 times 10 power minus 5 per second also, which is actually what I did here. That's why I can use A equals to lambda n. Over here, let me just erase this. You notice that here I'm using A equals to lambda n. The activity of my plutonium nucleus is 8.61 times 10 power 15. Okay. Wait. Oh, this one is power 15. I wrote here is -5. It should be power 15. Sorry. Okay. So your activity of your plutonium nucleus is 8.61 times 10 power 15. Your decay constant you already found from the previous question. What you're left with is to find the number of nuclei of plutonium that's involved, which is 1.097 times 10 power 24. Now, from here, if you want to find the mass of your plutonium, you take the number of nuclei multiplied by the nucleon number multiplied by your unified atomic mass. Now, nucleon number multiplied with your unified atomic mass gives you the mass of a nucleus. Nucleon number here is 236. You multiply by the unified atomic mass. This one gives you the mass of your nucleus. If you multiply with your number of nuclei, you're going to get the total mass. It's going to be 0.43 kg. Change to grams, which means you need to multiply by 1,000. You're going to get the answer as 430 grams. Okay, so this one should be okay. Right, then next one, last part, part C. Okay, wait, let me just erase this. Okay, the minimum electrical power required for the space probe is 0.84 kilowatts. Calculate the time in years for which the sample of plutonium-236 will provide sufficient power for you. Okay. So what you understand was that your plutonium nuclei must decay to produce your alpha particle, and the alpha particle itself produces the energy required for your space probe. So let's just say this now. If I want to talk to you about the nuclei, the plutonium nuclei, if I talk to you about the plutonium-236 nuclei, if I talk about the number of plutonium-236 nuclei with respect to time, the number will actually drop with time following an exponential curve like this. Okay. I can also say that the activity of the plutonium-236 nucleus will also decrease with time following the same graph. Okay. Now, it is because of the decay of your plutonium nucleus that gives you your alpha particle, which in turn gives you your power. So you could also say this. If I'm talking about the power that I can get from the plutonium nuclei with respect to time, it's actually also going to look like this. It's also going to be an exponential decay curve. Okay. Because what you understood was that your plutonium nucleus decays to give alpha particle, which in turn produces electrical power. Okay, so you have less plutonium nuclei, obviously you're going to have less alpha particles, which in turn means you're going to get less power. Okay, so if your number of plutonium nuclei or your activity decreases with time, it is reasonable to say that your power will also decrease with time. Okay. Now, one of the things that you learned in the notes was that when it comes to the exponential decay of a radioactive nuclei, you have a certain equation that you can use to describe the graph. It could be either n equals to n naught exponential negative lambda t, or a equals to a naught exponential negative lambda t. Now, the thing here is that you can actually say that activity is actually proportional to your power. They are directly related. It is the activity that gives you your power. You need to say it is the plutonium nuclei decaying that gives you your power in the first place. So you can actually say that activity is proportional to power. Okay, so from here, you can then say that in my case here, where I get this graph, I can also say that power is P naught exponential negative lambda t. Okay, this is the equation that will represent the power with time. So the thing here is that they tell you the minimum electrical power required for a space probe to operate to function is 0.84 kilowatts. So say this one is 0.84 kilowatts. You originally started off with what 1.9. This is power in kilowatts. You originally started with 1.9. And then after that, over time, it will decrease to 0.4. This is the minimum that your power space probe requires. After that, your space probe cannot move anymore. So what they want to know is how much time would it take for you to reach here? What is the time that is taken? So you use this equation, okay? So the workings will be a naught exponential negative lambda t, where you say the power is actually proportional to your activity. So P is P naught exponential negative lambda t. Then you sum in your values. The final power required is 0.84. The initial power is 1.9. Then exponential negative 7.85 times 10 power 9 times t. Then after that, your answer will be t equals to 1.04 times 10 power 8 seconds. Change to years, you're going to get 3.34 years. Okay. Now, because this one is in per second, This one must be second. All right. The units are actually identical. When it comes to the lambda t that you see here, the units must be identical. If the lambda that you used before this is in per second, t must be in seconds already. Okay. So that one is one part. Okay, so your final answer is 3.34. Yes, just like that. All right, so this question is done. Next one will be page 5, if I'm not mistaken. Okay, so I'll just clear everything here and then we go to page 5. Okay, page 5. This is November 15 P41. Okay, page 5, November 15 P41. Okay, this one will be question 8. All right. Now, distinguish between an atom, a nucleus, and a nucleon. What is the difference between a nucleus and a nucleon? A nucleus is just the small central core of an atom. It consists of nucleons. So a nucleon, on the other hand, is a particle contained within a nucleus, which is either a proton or a neutron. Okay? So this is what a nucleus and a nucleon actually mean. All right? Now, sometimes you hear the word nuclei also. Sometimes you see they say nucleus. Sometimes you see they write nuclei. Nucleus is the singular noun. Nuclei is a plural noun. Meaning this one is just one only. Nuclei is many. Nucleus. Okay, so that's really the difference between nucleus and nuclei. Nuclei is the plural form of nucleus. It means many nucleus. That's all there is to it. Okay, in case you're wondering what is a nuclei. Okay, now for part B, radon gas is a naturally occurring radioactive gas with a half-life of 3.8 days. The activity of radon gas in room is found to be 97 becquerels in each 1 meter cube of air. Calculate the decay constant per second of radon. When you see becquerel, as I mentioned to you, is a unit of activity and is specifically referring to per second. Okay, so becquerel here already is in per second. They ask you to find the decay constant. Lambda is ln2 over half-life, which is the equation that you used just now. So you take ln2 divided by your half-life, which they've given you in days, multiply with 24 hours, multiply with 3,600 seconds, you're going to get the final answer as 2.11 times 10 power minus 6 per second. This is your decay constant in per second. Then the number of radon atoms giving rise to activity of 97 becquerels, you just make use of A is lambda n, so activity is 97, decay constant is 2.1 times 10 power minus 6, multiply with n will be 4.6 times 10 power 7. So that one will be this, okay? Again, just make sure your units are consistent. This one I'll just make sure the units must be consistent. Must be consistent or similar. You see your activity here, 97 becquerels is actually per second. Your decay constant here is actually per second. You see they are actually consistent or similar to each other so that eventually they cancel off. if you notice that the units are not consistent, you need to change one to be the same as the other. Okay, just so you know. Okay, right. So number of nuclei is this value here. So that one is okay. Then I move on to the next part. Okay, next part is where they tell you that you have a volume of 2.5 times 10 power minus 2 meter cube of air in a room that contains 1 mole of molecules. If you have this volume of air, you will have 1 mole of molecules. Determine for 1 meter cube of air the number of radon atoms to the number of air molecules. Okay. So in your case, in 1 meter cube of air, your number of radon atoms is already found to be 4.6 times 10 power 7. Because this is what you found in the previous question. And this one was for 1 meter cube of air. So your challenge now is to find out what is the number of air molecules in 1 meter cube of air. So your number of air molecules, instead, right now, you need to find out how much it is. Okay, now here they already give you this. 2.5 times 10 power minus 3 meter cube. Sorry, not meter power 3, power 2 meter cube of air contains 1 mole, or rather 6.02 times 10 power 23 molecules. So what is 1 meter cube then? 1 meter cube, if you want to find out in terms of number of moles that you will have, it will just be 2.5 times 10 power minus 3 divided by 1.0. This one will be the number of moles you have. Okay. So if I wanted to find the number of N molecules, it will just be the number of moles multiplied with the Avogadro constant, which is what you're seeing here right now. For 1 meter cube of air, your number of N molecules is actually, terbalik. My case is terbalik. This one I did it wrongly. If 2.5 times 10 power minus 2 meter cube contains 1 mole of air, how much is 1 meter cube? You actually take 1 divided by 2.5 times 10 power minus 2 to get it in terms of number of moles. Sorry, my mistake. Okay, so 1 meter cube divided by 2.5 times 10 power minus 2 gives you the number of moles. Then you multiply with your Avogadro constant to get your number of air molecules. Just like that. Okay. Therefore, your ratio is number of radon atoms to number of air molecules. You're going to get the final answer as 1.91 times 10 power minus 18. That will be your final answer. Okay, so that one is done. Next one will be page 7. Then 9 also. Okay. Right, next one would be page 7. So this one, let me just clear it off. Page 7. 7 again, we can just do very quickly. Page 7. This is November 2015 P43. Okay, this one, page 7, define what is binding energy. I think we did this before in some of our questions before this. I think you can just copy it from your notes. It's just the energy needed to completely separate a nucleus into individual nucleons completely to infinity. This one is something that we know already. You can just take the time to copy from your notes later. Okay, part B. Data for two isotopes of uranium are given here. Then they ask you in the first place, state what is meant by isotopes. Isotopes, you actually learn the definition in AS physics. It is actually atoms of an element that have same number of protons but different number of neutrons, or same proton number but different neutron number. So you can actually just say something like this: different forms of the same element or nuclei that has the same number of protons but different number of neutrons. You can also say same proton number but different neutron number. Okay, so that one should be okay, just like this. Okay, so if this one is okay, then after that you need to complete figure 9.1. Complete figure 9.1 that you have here. Okay, so they give you binding energy per nucleon and they give you binding energy. So binding energy per nucleon is actually just binding energy divided by your nucleon number. So here you can actually just easily work out what is binding energy. Binding energy would just be binding energy per nucleon multiplied with nucleon number, giving you this value. Okay, this one will tell you BE is BE per nucleon times nucleon number. That's all there is to it. All right. And then the second row, you want to find binding energy per nucleon. Take binding energy divided by your nucleon number, which is 1082 divided by 3238, giving you 7.57 mega EB. Okay, so this is very simple maths. So this one, no issues here. Okay, now uranium-235 has half-life of 7.1 times 10 power 8 years. Show that the decay constant lambda of uranium-235 is this value. So all you just need to do is, again, if they give you half-life and then decay constant, usually you will need to use this equation. Again, almost always, all right? So here they want you to find decay constant given half-life. You know you're going to use lambda is ln 2 over half-life. So it's ln 2 divided by 7.1 times 10 power 8. Again, change to years. Sorry, from years change to second. Multiply with 365 days. Multiply with 24 hours. Multiply with 3,600 seconds. Eventually giving you this value. 3.1 times 10 power minus 17 per second. Okay, so that one is okay. Now, the next one would be a sample of uranium. Next one will be detailed. A sample of uranium-235 has this activity. Calculate the mass of the sample. So the workings that you're seeing here is kind of similar to what you've been seeing before this. Find out the number of nuclei using A equals to lambda n. Okay, if you have mention of activity and then suddenly you have mention of mass, almost always you use this equation actually. A is equals to lambda n. So activity is 5 times 10 power 3 is already in per second. Decay constant that you found just now is already in per second. The units are actually consistent, so then you know they cancel off. There's nothing you need to do. Find out your number of nuclei is 1.613 times 10 power 20. Then move on to find your mass. Take your number of nuclei, multiply with nucleon number, multiply with unified atomic mass. This one is your mass of your nucleus. Okay. So you're going to get 1.613 times 10 power 20 times 235 times your U. And then after that, you're going to get the answer in kg, change to grams by multiplying 1,000. You're going to get the answer 0.629 grams. just like that. Okay, so that one is all right. Okay, now move on to the next one. I think the next one is page 9, I think. Wait, okay, next one should be page 9. Okay, so looking at page 9, this is March 16 P42. I think after this one is will be another different variation in the question. Okay, now let me just see from here. March page 9. Okay, right. So let's just do page 9 first. Okay, page 9, beryllium 7 is produced in the upper atmosphere and then sinks down into the Earth's surface. Nuclei of beryllium 7 decay with half-life of 523.3 days to form a stable nuclei. The activity of a sample of beryllium 7 on the 3D is 39 millibecquerel. So show that the decay constant of beryllium 7 is 1.5 times 10 power minus 7 per second. Find out the mass of beryllium 7 on the leaf. And then after that, these two I think is something that we can easily do. All right. Show the decay constant. Again, you have half-life and you want decay constant. So lambda equals ln 2 over t half-life. So ln 2 over 53.3 times 24 hours times 60 minutes times 60 seconds, you're eventually going to get the answer as 1.5 times 10 power minus 7 per second. All right, so that one is okay. Now, then after that, you need to find out the mass of beryllium 7. Again, you see, got mensual activity, got mensual mass. Almost always, you're going to use A equals to lambda n. So, n is A over lambda. Activity is 39 times 10 power minus 3. Where did the 10 power minus 3 come from? Is because you have milli here. Okay. Then you divide by your decay constant. Both again are in terms of per second, so there's no need to worry about your units. Eventually, you get 2.582 times 10 power 5. And after that, you get your mass. No? Your mass is number of nuclei multiplied with nuclear number times U. This one is again the mass of your nucleus. Then just add everything. So just multiply everything together. Eventually, you get the answer as 3 times 10 power minus 21 kg. Just like that. Okay. Right. So this is one. Okay, so this one is all right. You see, this first two question is always something that seems to be occurring for your past years, right? So it's something that you really need to know. Okay, now for part C, they tell you the leaf is covered so that no further beryllium-7 is added to the existing sample of the atmosphere. Calculate the time that must elapse before the activity of the sample is reduced to 2 millibecquerels. So your original activity was 39 millibecquerels. And then now they say it's reduced to 2 millibecquerels. They want to find out what is the time that has elapsed. You can actually use the equations. A equals to A naught exponential negative lambda t. So 2 millibecquerels is your final activity. 39 millibecquerels is your initial activity. Now you don't really need to bother about changing the units because you see this one is millibecquerel. This one is also millibecquerel. The units will actually cancel off. So you don't need to go through the trouble of changing the units. All right. Then exponential negative lambda t. So your lambda is 1.5 times 10 power minus 7. This one, if you recall, is actually in terms of per second. Your t here will be in units of second. Okay, so try to solve this by loaning both sides. You take 39, shift to here, you get 2/39. Then you ln this side, and then you ln the other side. But because you're lning e, you're just going to get a 1. And then you get negative 1.5 times 10 power minus 7t. And then after that, all you just need to do is to solve using whatever knowledge you have learned in maths. T is 1.98 times 10 power minus, 1.9 times 10 power 7 seconds. All right. Okay, this ln e here, as I mentioned, is just 1. All right, nothing to it.